So what is this golden ratio? Around 300 BC, Euclid, in his most famous book Elements, had several propositions and proofs regarding this ratio, which is now known as the golden ratio. According to one of the statements, he mentioned a straight line, when divided into two parts, when A being the larger part and B the smaller segment, something like this. Take the segment, divide it into two parts, A and B. So A plus B by A, this is nothing but the entire line segment divided by the larger part will be equal to the larger segment divided by the smaller segment, which is nothing but A by B. This is equal to the golden ratio. So what is the golden ratio? We usually denote with this Greek letter phi. Now, how do we find the value of this golden ratio? This is nothing but equal to 1.618033. It's an irrational number, so it continues. So how do we find the value? We divide this equation. You can see that A plus B by A is nothing but 1 plus B by A. So we know A by B is nothing but phi. So I can write this equation as 1 plus 1 by phi equals phi. Now you simply multiply by phi, you'll get a quadratic equation. So a quadratic equation comes out to be phi square minus phi minus 1 is equal to 0. So there are two roots to this equation. So one is 1 plus root phi by 2. The other is 1 minus root phi by 2. You can see that the second root is negative. We are talking about line segments here. So we want the ratio to be positive. So what we're going to do, we're going to take the first ratio, which is nothing but the value I've written here, 1.618033. 1 plus root phi by 2. So what's so special about this number? Look at phi square. If you try to compute this, this is nothing but 2.618033. Again, this continues. You can see that when you square phi, you're going to get the same decimal part or the fractional part. Right? So this is nothing but equivalent to 1 plus phi. If you take the reciprocal of phi, 1 by phi, you're going to get 0.618033. Again, this is nothing but phi minus 1. So let's look at the Fibonacci sequence. So we all know that we just add up numbers, the previous two numbers, to get the new number. Right? Just to note it down, we can say that f0 is equal to 0, f1 is equal to 1. Right? The next number will be 0 plus 1. So fn is nothing but the sum of the previous two numbers, f of fn minus 1 plus f of n minus 2. Correct? So simply to note it down, it's nothing but 0, 1. 0 plus 1 is 1. It continues 2, 3, 5, 8, 30, so on. We all know this sequence, it's very famous. So how does this relate to our golden ratio? Let's look at the ratio of any two numbers here. Right? I'm talking about a ratio that fn divided by fn minus 1. So we'll start from 2. So it's 2 by 1. You can see that this ratio is equal to 2. Let's take the next pair. It's 3 and 2. So 3 by 2. This is nothing but 1.5. Next, we have 5 by 3. So this is nothing but 1.66. Next 2, so it's 8 by 5. So if you divide 8 by 5, you're going to get 1.6. Now you can see that we are already coming close to this golden ratio. We are at 1.6 now. So next is 13 by 8. So this is nothing but, let me just calculate, 1.625. So we are around 1.6. Let me take some higher numbers like f20 and f19. Let me see what that ratio is. I'll just give you what is the value of f20. It's nothing but 6765. And f19, that is nothing but the 19th number in the Fibonacci sequence. So it is 4181. Okay. Let's look at what this ratio is equal to. 6765 divided by 4181. You might be surprised, this comes out to be 1.618033, then the later numbers are not exactly matching to golden ratio, but it's close, right? You can see the accuracy here. We are already at the 6th decimal. So why does this happen? And we can even say that if you increase the number, that when the n tends to infinity, say fn by f of n minus 1, that is the number fn and fn minus 1 in the sequence, will be equal to the golden ratio. Now look at these numbers. What we are doing is we are just taking the sum of the terms divided by the previous number. It's similar to the ratio we have looked at. So a plus b by a, right? The sum of the two numbers divided by the number. So you can see that, you can see golden ratio here also. There are a few more examples where you can find the golden ratio. You can look at nested fractions. For example, you take this fraction 1 plus 1 by 1. Okay, this is nothing but 2. So this is equal to 2. So if I continue this fraction now, look at it. So it's 1 plus 1 by 1 plus 1 by 1. I just want to continue the same sequence. What is this sum equal to? Just look at this. This is 1 plus 1, this is 2. So 1 plus half, which is nothing but 3 by 2. Now if I take the next fraction, 1 by 1 plus 1 plus 1 by 1 plus 1 by 1. Now let's try to compute this one. So this is 1 plus 1 by, we have already calculated this part in the previous. This is nothing but actually 3 by 2. So I can directly write this as 3 by 2. Okay. So this is nothing but 1 plus 2 by 3, which is equal to 5 by 3. So you can guess what the next two numbers would be. It is nothing but 8 by 5, then it will be 13 by 8. This would continue. Can you see the numbers? These numbers are nothing but the numbers of your Fibonacci sequence, right? So how is it related to golden ratio? Look at this equation now. Suppose I take x is equal to the same sequence, right? 1 plus 1 by 1 plus 1 by. Because we know that the ratio is not exactly the golden ratio unless we take a large number, right? Or go up to infinity. So I'm going to try the same. I'll keep on adding this sequence up to infinity. Now, because it's a nested fraction, we know this sum here is nothing but x itself. So we come across the quadratic x is equal to 1 plus 1 by x. If you solve this quadratic equation, what you're going to get is the golden ratio again. Even the solution for this nested fraction is nothing but 1.618033, so on. So you need not really take these numbers of Fibonacci sequence. You can actually take any other series. You can start with 1 and 3. But if you keep continuing adding the numbers, you can see that the ratio will still remain the same, something like a plus b by a. So if you take very huge numbers in the same sequence, you're going to get the golden ratio once again. So using this golden ratio, we have many other objects like golden triangles, golden rectangles, golden spiral. All these are somewhat related to these numbers, right? What we do is we find out a plus b and then divide it by the larger segment, which is a. So the golden rectangle is nothing but we take one of the sides as a plus b, the other side as a. The ratio of a plus b by a is again the golden ratio. So when we look at it, it's pleasing to the eye. But in daily life, we associate golden ratio with many things: shells, sunflowers, plants, trees, etc. So the ratio there might be around 1.5 to 1.7. It varies. It is close to 1.61, but not exactly true, right? So sometimes we exaggerate what golden ratio is. So if you like the video, please click on the like button and share it with your friends. For more fun videos like this, please subscribe to the channel. Thank you.